In this video, I will talk about a nonlinear system that is derived from this tunnel diode circuit. So this circuit is called a tunnel diode circuit because there is a diode that is a tunnel diode. And next I will introduce the stuff in this circuit first. So this is a battery, and this is a resistor. And if we denote the current flow through the resistor as I, and the voltage decrease along the direction of the current as V, and then V and I satisfy this relationship. Here R is a constant. It is a number that is called the resistance of the resistor. And this is an inductor. And again, if we denote the current flow through the inductor as I, and the voltage decrease along the direction of the current as V, then V and I satisfy this equation. Here dot means di dt. So differentiate I with respect to t, and so I dot is the rate of change of the current. So L is a constant, it is a number, it is called the inductance of the inductor. Next, we have capacitor. So again, if the current flows through the capacitor is I, the voltage decrease along the direction of the current is V, and I and V satisfy this equation. Here C is a constant that is called the capacitance of the capacitor. So here the quantities of V and I are related by a number, so these relationships are all linear. So for the diode, so this is the tunnel diode, and so one thing about the diode is that the current only flow in one direction. So the current can only flow this way, it cannot flow the other direction. And when the current flows through the diode, and the relationship between the current and the voltage decrease along the direction of the diode is given by this equation. I equals f of v. And f is not a linear function anymore. F looks like something like this. So this curve describes a tunnel diode, and when V is negative, the current I is just 0. So now we will try to write down a differential equation about this circuit. So let's look at the known quantities. So the battery voltage is known, the resistance R, and inductance L, and capacitance C are known, and this tunnel diode is also known. Its characteristic is given by this function f. And the equation that we want to write about is about unknown current I in this part, in this line, and the voltage decrease between those 2 points. So the voltage decrease over capacitance or over the tunnel diode. So let's first write down an equation about the voltage. So over the battery, the voltage increases is E, and then it decreases back. So it is equal to the voltage over R, and the voltage over L, and then V. And the equation about the current is that the current flow on this line comes from 2 branches. One is from the capacitance, that's the current, and one is from the diode, which is FV. What I will do next is graph this function of V, graph the voltage V and I as function of t using the Euler method. So with this differential equation, we know the relationship between the rate of change and the current value. So we can start with the initial value and plot the subsequent points. And by looking at the graph, I'll try to make 2 points. So one is when t goes to infinity, eventually the V and I stabilizes. They stabilize. So actually, this will stabilize very quickly. And the second point is I will adjust one parameter, that is the voltage of the battery, and I will increase the voltage, and then what we want to see is a sudden jump of the graph of the voltage V. Before we see the graph, there's one thing that I need to mention is that in order to plot the points, we need a function f. Right now it is something just like this. We need a specific formula for the function f. And what I will do is using some straight lines to approximate this function. So this will be my f. It will suffice to demonstrate the point. So here the horizontal axis is the voltage and the vertical axis is the current, and this graph describes the current and the voltage relationship for a tunnel diode. And we don't really care when the voltage is negative, and when voltage is positive, this line extends infinitely. The choice of coordinates here, 50 or 100, and the choice of the number here are random. We don't really care about the unit right now. And these numbers are chosen so that the graph looks good. And with this f, this is the graph of voltage and current. So blue line is voltage, the red line is current. The vertical axis could represent the voltage or current. The horizontal axis is the timeline. And again, there's no unit, so you don't really know how long is this time. And so this graph is for resistance 10, capacity 100, inductance, and the battery voltage. And the step here is the step for the Euler method. This is the initial value of voltage and current. What I will do next is increase the battery voltage by 10. I click this button, it will increase the battery voltage by 10. And let's see what happens. See, as we increase the battery voltage, so let's focus on the blue line, which is the voltage that we care about. So as we increase the battery voltage, which is a parameter, the solution increase a little bit. Until at one point, it suddenly jumps. This is the behavior that I want you to see. So let's increase the battery voltage by 1 at a time. We still see this sudden jump. Now, let's increase the battery voltage by 0.1, and I change the scale to draw more points. And we see a sudden jump for the blue line. Let me decrease it. Just suddenly increase it, decrease it. Usually, the solution depends on the voltage continuously, but at one point, there's a sudden jump. This is the behavior that we want to see. I want you to see. People usually don't know how to solve nonlinear ordinary differential equations. And what people usually do is analyze the solutions, understand the system by looking at the equations without solving them. So I will demonstrate here that we can just by looking at these two equations and see and predict the sudden jump of voltage V here as we increase the battery voltage E. So here I will assume that we already know that as time goes on, the system stabilizes, the V will become a constant and the current I will become a constant. So basically we are taking t to infinity in both equations, and we know that because I and V will be just numbers, they are constants, and the derivative of them will just become 0. So these two equations becomes these two equations. So here I and V are the stabilized value of current and voltage, and these are just like ordinary equations. There's no derivative there, and we can solve these two equations by graphing them together. We first draw the graph of I equals FV, and then notice this is a straight line. The horizontal intercept is the voltage voltage E. When E is small, these two equations has one intercept that gives us the voltage V. And if E is big, it gives us another intersection point, V prime. And then I don't think I can explain it very well, but you should try to convince yourself that if I increase E, the battery voltage from this value to this value, this straight line will move to the right, to this line, and the V we care about will increase, but it will never move to V prime continuously. The intersection point will move continuously, but at a certain point, it will have to jump to a point like this, and then the intersection point will move continuously. So next, we will see this process of increasing the voltage voltage E in simulation, and we will see when does this jump happen. Okay, so here the initial value of V0 is 10, and the initial current is 500, and we will increase the voltage, and we will pay attention when does it jump. Oh, so the jump happens so when you have 3 stable points and the voltage jumps from, this is 50, so this intersection is about 50, to this is 150 to 150. So the stable value of voltage V jumps from this point to this point. Okay, now let's change the initial value of current to 50, and the battery's voltage start from 100, and let's repeat this process. So let's increase the battery voltage. Let's see when does the jump happen. So now the jump still has not happened yet, but as I increase E, we can see that right now this is the stable point. So the value is, the V is 50 and here, and as I increase E, this cannot be the stable point anymore. So it has to jump to this point. So let's see. We see the jump. Because you only have one stable point, you have to jump now. Now let's change the battery to 100 and the voltage to 100. Okay, so the initial voltage V is 100 and the current is 500. Let's increase voltage V and see what happens. We already have a jump. Let's see again. So you see that the voltage originally stabilized at 25 something, so 25 here, and as I increase the voltage of the battery, it jumps to 100. So as soon as you have two stable points, the jump happens.